So we've seen now that when a material becomes magnetized, either because a magnetic field or a current is sent through it, then we establish bound volume current densities and bound surface current densities within that material and across its surface. So we're now ready to put everything back together. So we're now going to be considering the field which can be attributed to these bound currents, as well as the field due to everything else, which we'll refer to as the free current. So it's possible for the free current to flow through the substance itself if it's a conducting material, or alternatively, the free current could flow through wires which have been embedded within the magnetized material. So in order to write down equations to describe this, we'll follow a very similar method to what we used when we were considering the bound and free charges with the electric displacement. So we are going to write that our volume current density J is equal to the bound volume current density, which is that current density due to the magnetization, plus the free current density, which is the current due to everything else. So the types of things that are going to cause our free current are if we hook up our material to a circuit and use a battery or a power supply to send current along it. Then that is a form of free current where the charge carriers are actually moving all the way through the material. Now, what we can do is use Ampere's law, and we can write this as J is equal to the curl of B divided by mu naught, where B is the magnetic field. And we've just said that J is due to the bound current density plus the free current density. And we saw over here that the bound current density was the curl of the magnetization. So we can write this as the curl of the magnetization plus the free current. So this means that we can write down an equation for the free current. We are going to be using this part of the equation along with this part of the equation. So this tells us that the free current is equal to the curl of the magnetic field over mu naught minus the curl of the magnetization. And so we can pull the curl out the front, and we've got the curl of B over mu naught minus the magnetization. Now, we call this part here our H vector. It actually doesn't have its own name, so it's the auxiliary field H, but people usually just call it the H vector or H. Okay, so H is equal to B divided by mu naught minus M. And let's put that in a box because it's an important equation that we will be using again and again. Now, this allows us to write down a form of Ampere's law in terms of the free current. So we can write that the free current is equal to the curl of H. And this is known as Ampere's law for free current. Now we can use Stokes' theorem to write down an integral form of this as well. So the field we're using this time is the H. So we've got that the surface integral of the curl of H dot dA is equal to the integral around H dot dl around the loop. And we can also say that because the curl of H is just the free volume current density, that we can replace this inside the integral with just the free current density. So this is equal to the free current density dot dA. And then we know that the current density times that cross-sectional area gives us the current which is flowing through that surface. Now, because physically this is the integral of the volume current density across the area of surface, and remembering back to how we defined volume current density, the volume current density times the cross-sectional area just gives us the current which is flowing through this surface. So in this case, this is equal to the free current which is enclosed within that surface. And so this lets us write down Ampere's law in the integral form, which tells us that the integral around a closed loop of H dot dl is equal to I times the enclosed free current. So this is another useful equation. So the H vector plays an analogous role to the D vector, the electric displacement, in the electrostatic case. So in the electrostatic case, the D vector allowed us to express Gauss's law in terms of the free charge alone. In this case, the magnetostatic case, the H vector allows us to write Ampere's law in terms of the free current alone. And why that's useful is the free current is what we can actually control. This is the current that we add to the circuit, and the magnetization and resulting bound currents just happen as a result of the magnetization that this causes. So we have no control over that, but we can control how much free current we add into a system. So let's have a look at an example problem now. So in this problem, we have a long copper rod of radius r that carries a uniformly distributed free current I along its length, and we're asked to firstly find H inside and outside the rod. So let's start by drawing a diagram showing what's going on. So here is our wire, and it's got a radius r, and it's carrying a current along like this. And our first job is to find H inside. So in order to do that, we're going to make use of Ampere's law for free currents, because we've been told what the total current is. So by taking an appropriate Amperian loop, we will be able to work this out. So let's take an Amperian loop inside with radius little r, and then we've got Ampere's equation that H dot dl is equal to the free current enclosed. So the amount of current enclosed within this loop, because the current is uniformly distributed, is going to be equal to pi r squared times the sigma, the surface current density, which in this case is going to be equal to pi r squared times the total current, which is I, divided by the total surface area, which is pi capital R squared. So those pi's will cancel out, and this will equal I little r squared over big R squared. And then considering this part of Ampere's equation, we can assume that H is going to be constant around this loop because of symmetry. So we've just got H times the integral around the loop, which is just the length of the loop, which is the circumference of the circle. So this is, which is equal to H times 2 pi r. So what we're going to do now is equate this with this to get our expression for H. So this tells us that h times 2 pi r is equal to I little r squared over big R squared. We can cancel out one of those r's, and this tells us that h is equal to I r over 2 pi r squared, and this is for r is less than or equal to capital R, because this is inside, i.e. inside. Now, outside, we're going to use a very similar approach, except that we will choose our Amperian loop like this one, where it goes all the way behind. And so in this case, we can write that H dot dl is equal to the free current enclosed. But in this case, the free current enclosed is just going to be equal to our total current, and the length of the loop is once again equal to the circumference of the circle. So again, this will be equal to h times 2 pi r. And so putting this together, we end up with h is equal to I divided by 2 pi little r, and this is for r is greater than or equal to big R, so i.e. outside. Now, another thing that we can say about outside is that we know that outside there is no magnetization, because there is no material out here to be magnetized. So outside, we know that H is equal to B. So outside, well, H is equal to B divided by mu naught. So that tells us that B in this case would be equal to I over mu naught times 2 pi r, which would be familiar to you as the equation for the magnetic field due to a long current carrying wire. Now, the question has also asked us, given that metallic copper is weakly diamagnetic, comment on the direction of B, M, H, JB, and KB. So let's sketch that on another diagram over here. In this case, we've got our current going up like this, and we know from our right-hand rule that that is going to result in a magnetic field vector which is going around like this, so B. And so this is going to, so B is going to be circumferential. And so if we're thinking about spherical or cylindrical coordinates, then this is going to be in the positive phi direction. And if we now think about M, the magnetization, because this is diamagnetic, the magnetization opposes the magnetic field. So the magnetization is actually in the opposite direction. So we have got that M is going this way, and so M is also circumferential, but it will be in the negative phi direction. And then if we think about H is in the same direction as B and the opposite direction to the magnetization. So those both work in the same direction in this case. And so H is also going to be in the same direction as B. So it will be around like this. So H is circumferential, and it will be in the positive phi direction as well. And then we're asked about the volume current density. And So then we're asked about the volume current density, and the volume current density is the curl of the magnetization. So you can just use your right-hand rule to get the direction for JB. It's going to be going in the opposite direction to the current. Alternatively, you know that in diamagnets, the magnetization opposes the current, so it needs to be in the opposite direction. So JB is anti-parallel to I. So we can call that, if we want, in the negative Z direction, if we say if I is positive Z. And then we're asked about KB, the surface current, and we know that the surface current is M cross N. So let's consider a little piece on the outside here. You can see here that the magnetization is coming out of the screen, and the normal vector is to the right. So combining those with your right hand rule, you can see that KB is going to flow up the outside of the wire. So KB is in the plus Z direction. So it's not a bad idea to add direction to our values for H here to make them into vectors. So we can do that by adding phi here and also a phi here, and then those are both vectors. Now it asks us, why is metallic copper diamagnetic when copper has 29 protons? So because copper has 29 protons, it should also have 29 electrons, which is an odd number of electrons. And previously we said that atoms with odd numbers of electrons tended to be paramagnetic, whereas in this case, this is diamagnetic. Well, that's true for a single atom. If we had a single atom of copper, it is going to behave as a paramagnet. However, it turns out that when you bring lots of copper atoms together, we get metallic bonding. And those sole electrons in the outer shell form an electron C, and they're free to move within there, which allows this material to behave as a weak diamagnet rather than a paramagnet. So one thing that you may have already noticed, or if not, I encourage you to pay attention to, is that physicists tend to talk about H a whole lot more than they talk about B. But in the electrostatic case, they tend to talk about E rather than talking about D. So why is this? Well, it's really because physics is an experimental science, and it's much easier to measure H and measure E because of the types of instruments we have and how we set up fields. So in a laboratory, it's easy to measure and control the current, and generally when we are setting up magnetic fields, we set them up by sending a current. Now, it's much harder to measure the magnetic field as this depends upon the material used, and if it's a ferromagnetic material such as iron, then it possibly depends upon the history of that material as well. So measuring the magnetic field B is actually quite hard. However, it's easy to measure the amount of current going in, and the amount of current we put in relates to H. So this is why it's easier to get a measurement of H rather than B, and we talk about it preferentially. On the other hand, with electric fields, it's very easy to measure and control the voltage. There's lots of sources that we can use that give a fixed voltage as the output. On the other hand, it's very hard to measure the exact number of charges on a plate. And if we wanted to measure D, we'd need to be able to know how much charge we have in a certain location. And that measurement is very hard to get. However, if we set up a certain voltage, then we know what electric field that voltage gives, because we know that the electric field is just the negative of the rate of change of the voltage. We've got that E is equal to minus grad V. So that is very easy to measure when we measure the voltage. So just as in the electrostatic case where we had to be careful about taking the analogy between E, the electric field, and D, the electric displacement, too far, we also need to be careful in the magnetostatic case. So in the magnetostatic case, we've seen that we can write Ampere's law as the curl of B is equal to mu naught J, where J is the volume current density. And in terms of H, we can write this as the curl of H is equal to the bound current density. And we can do this in both the differential and the integral form. So you might start to think, well, in that case, H is really just like B, except that we need to account for this factor of mu naught. And we know that the divergence of the magnetic field is equal to 0. So does that mean that the divergence of the H vector is also equal to 0? Well, this is very much not the case. How we can see it's not the case is by considering this equation over here. So using this in the equation, we know that the divergence of H is equal to the divergence of B over mu naught minus the divergence of the magnetization. And we've said that the divergence of the magnetic field is 0. So this one here does go to 0. But this thing is not necessarily equal to 0. So we can't assume that the divergence of H is equal to 0. Now, one place that we can see this relatively clearly, which you should be somewhat familiar with, at least from high school and everything, is in a bar magnet. So here's my bar magnet. I'm going to make this end my north pole and this end my south pole. And my magnetization is going to be going in this direction here. So this is my magnetization. And what I'm going to sketch on now is my magnetic field lines. So hopefully you remember how to do this for a bar magnet. They're going to look something like this. They come out this end and they go in at this end. One's going to curl up there, curl up there, curl down there, curl down there. This is all symmetric. I just haven't done a brilliant job with drawing it. And that's going that way, that way, that way. And then we've got around here like this as well. So that shows our magnetic field lines and our magnetization of the bar magnet. What we're going to do now is consider, well, what does H look like? So what I'm going to do is I'm going to copy this and then edit it to make it into H. So let's copy this and we'll paste it over here. Okay, and now we will do H in green. Now, outside the magnet, the magnetization is equal to 0. So here, M is equal to 0. So we can see from this equation here that when the magnetization is equal to 0, H is just equal to B over mu naught. So it's all just going to be going in the same direction. So my H field is going to be on top of my B field out here. So this is going to be going like this in the same direction. However, inside you can see that the magnetization is not equal to 0, and we're actually going to assume that the magnetization is bigger than B over mu naught. So in this case, the H is going to be in the opposite direction to B, because this is going to be a negative. So inside, if we sketch what happens, inside it goes like this, and it is going in this direction here. It's going in this direction here, in this direction here, and in this direction here. So it actually curves outwards a little bit here, whereas this one here, if we drew it accurately, it curved inwards a little bit. So this shows you what H looks like around this bar magnet. And one of the things to note is that we have sources here. There are H lines emerging from here, and this part acts like a sink. So this is these 2 points here and here on the bar magnet. We definitely do not have that the divergence of H is equal to 0, because we have a source and a sink. And the same can be said for the magnetization, because the magnetization is 0 out here, whereas it's got a value in here. So again, this is going to be a sink for the magnetization, and this end will be a source for the magnetization. So these things are not always 0.